We'll continue in the gradient vector calculation through a spherical coordinate and and Cartesian coordinate that we are seeing. So we are using parametric vector technology as far as the calculus is concerned. So we will move more into the kind of calculation of the gradient vector, historical calculation in a way that first time we are kind of, otherwise we were doing Cartesian coordinate, algebraic equation, calculus. The next step came as Cartesian coordinate, algebraic equation, calculus, multivariable. Now we have a spherical coordinate, we have Cartesian coordinate, and we have parametric vector, parameterization of the vector. So now then multivariable and then calculus. So things are kind of, it is growing in a kind of a broader way, minute and broader. The scenario is happening, the calculus is changed to this state, calculus is changed to this state because of artificial intelligence. The way we have tons of features and then we see as non-collinearity among the features. This is what is expected as far as machine learning is concerned. That features what we see in the machine learning, they should be means there should not be any collinearity, non-collinearity among the feature, orthogonal features. So when the dimension of feature, number of the features in the machine learning or artificial intelligence, then it grows more than 3, then problem starts. So multivariable means not 1 to 3, it may go up to 100,000 features like that. So in those scenarios, how we can tackle it? Now we are in a phase of calculating the gradient vector. So gradient vector is a vector that is also called velocity vector. Velocity vector in the sense like rate of change. So that is the first derivative. If I have if I have y equal to fx, then dy by dx, y equal to fx function over x, then dy by dx along I direction. This is x axis, this is x axis, this is y axis, this is y axis, this is x axis. With x as independent component, y is dependent, and y equal to fx. In that case, dy by dx along x-axis, dy by dxi is the gradient vector along I direction. If I have a function fxy, then dy by dxi d I'm sorry. If function is fxy, function over x comma y, function over two independent variable x and y, that is z equal to fxy, then dz by dxi plus dz by dyj. So dz by dx and dz by dy are two xy components of the gradient vector. Vector has components x, y, z. So dz by dx, dz by dy are two components of gradient vector. Now, if I have a density function fxyz, then dfxy d equal to fxyz, d equal to fxyz, that is the density function. Then dd by dx, d means capital D, that is density function. dd by dx, dd by dy, and dd by dz are the three components of the gradient vector as far as density function is concerned. But what about the gradient vector direction? That is always in a kind of confusion. So now for that simplicity, now we go with the spherical coordinate. So a spherical coordinate, we have a kind of a sphere. If I have a sphere, so I have a sphere. If I have a sphere, then this is center of the sphere. I have one sphere and this is the center middle. If this is the sphere, then at the center of the sphere, then if I draw a radius, then from vertical it makes 5 degree. If this is vertical and this is the radius along any point in the sphere, then from the vertical this angle is 5 degree. If that is true, then vertical component is, if radius is a, then a cos phi, whereas horizontal component in xy plane it is a sin phi. What about x component is sine phi cos theta, where it rotates in xy plane like this. So if I have radius like this, then from vertical it makes 5 degree. And so vertical component is a cos phi, a sin phi falls in xy plane. Now if this is x-axis, then it makes theta from the x-axis when this a sin phi, where a sin phi falls. So that is theta. If I rotate theta 2 pi, then theta rotates 2 pi, whereas phi from vertical it rotates 0 to pi. So this is phi and this is theta. So theta rotates 2 pi. So okay, so that is the scenario that we saw. So at any point on the sphere, if I take coordinate as a spherical coordinate, then it will be r, or if it is a full plane radius, then a, and then phi, a, phi, and theta. So those are the three independent component now that we are seeing, a, phi, and theta. Like if it is Cartesian coordinate system, then any coordinate is specified by x, y, z. Now any point is specified by three independent component r, phi, and theta, or phi, r, theta. So that is the scenario. That scenario we are seeing. If I convert this spherical coordinate to Cartesian coordinate, then it will become, the x component will become a sine phi cos theta, a sine phi sine theta, and a cos phi, a sin phi cos theta I plus a sin phi sin theta j plus a cos phi. So those are the three components. Now it's easy, right? Means if I have a vector, if I have a kind of now if I have a parametric vector, any vector, either it is parametric vector, vector field, magnetic field, electric field, electromagnetic field, velocity field, acceleration field, and this field and that field. Whatever, if it is a vector, it has components along y-axis, z-axis, k-axis, where whatever the kind of the coordinate system we are following. So if I am in Cartesian coordinate system, then it has three. If it has three dimensions, then it has three components. So x component is a sine phi cos theta, y component is a sine phi sine theta, and z component is a cos phi. If if this is kind of this is what the kind of scenario is. So a sine phi cos theta, a sine phi sine theta, a cos phi. Okay, so now we are kind of we will bring the sphere and then we'll proceed probably. Okay, so this is our sphere is back. So we will proceed. So like I talked about any point on the sphere. So any point on the sphere, the independent component is any point on the sphere. The independent component is r, phi, and theta. And if I talk about the Cartesian coordinate of the point, then x component is a sine phi cos theta, a sine phi, phi a sine phi falls in xy plane, whatever theta degree it is making from the x axis. So a sine phi cos theta x axis, a sine phi sine theta is y axis, and a cos phi is z axis. So, 3 we have received. Now, we are free to move ahead in calculating the gradient vector. Okay. So, if I talk about the gradient vector, then if I have three coordinates, if I have, okay, so I consider the inside the this sphere there is a origin. So if there is origin, then this point, okay, in Cartesian coordinate, this point is a sine phi cos theta I, a sine phi sine theta j, and a cos phi is the k. So that is what. Now if I wanted to calculate the gradient vector, then I have to differentiate it with kind of some independent variable. Now suppose that I keep r as constant and theta as constant. This is what we are doing. So if this is the r and this is phi, this is r and this is phi, and if I say sine phi, it falls in on x-axis. From x-axis it is making theta wherever it falls. So suppose this is r and this is phi. If it falls on x-axis, it falls here. Can you see where it is? Now from x-axis it is making theta. If that is the case, then if it is a, then a sine phi cos theta is x-axis, a sine phi falls wherever, sine theta is y-axis. If that is the case, now let's consider that a, the radius is constant and theta is constant wherever it is. So we are moving in a phi plane, means we are moving in kind of a plane where the on xy plane it is theta angle from the x-axis, and then if phi, only phi is changing, radius is constant, theta is constant. If theta is 0, then it is pure xz plane. If theta is 0, then it is pure xz plane. If theta is 0, if theta is 0, if this is x-axis, this is y-axis, if this is x-axis, if theta is 0, then it is pure xz plane. If theta is 90 degree, then it is pure xy plane. If theta is 0, if theta is some angle, then that is the, it has x, y and z. So it is in x, y, z plane. Now if I rotate phi, then it will, keeping the theta constant, it will rotate like this, and where radius is constant. If theta is 0, then it is pure xz plane. If I rotate phi, it would rotate like this. If I keep theta as 90 degree constant, then it will rotate purely in the yz plane. If there is some theta, then xyz plane, if I rotate the phi keeping theta and r constant, then it would rotate like this. This is a spherical coordinate system. Now I have x component as r sine phi cos theta. Now if I try to find out the gradient when phi is variable, then it will become r cos phi cos theta. That is the I. Now j is r cos phi sine theta, whereas k is minus a or r minus a sine phi. So x component is a sine phi cos theta, that becomes a cos phi cos theta. Y component is a sine phi sine theta, that becomes a cos phi sine theta. Z component is a cos phi, that becomes minus a sine phi. So this is the gradient vector, and it has three components: a cos phi cos theta, a sin phi sine theta and minus a sine phi. So these are the three components of gradient vector. Now consider that if okay, now consider it is at theta degree from the x-axis. If it is theta degree from the x-axis, then this is phi from the vertical. Now if I take sine component, then it falls on the xy plane. So if I consider this vector as any vector called r or any vector alpha, okay. Now alpha a phi, A sine phi has a direction called alpha. Alpha is a vector. Alpha has x component, alpha has y component. Alpha x component is alpha cos theta, y component is alpha sine theta. If that is true, now we are in alpha z plane where phi is variable. Only phi is variable and we are in alpha z plane. Now if we see closely the gradient what we have calculated, that is a cos phi sin a cos phi cos theta I plus a cos phi sin theta j. These are the components along I axis and j axis. If I add these two, then it becomes alpha. This is what we are talking now. Because I, j are component of alpha 1. So it becomes a cos phi and in braces that a cos phi and then in kind of a cos phi. And whatever we are saying cos theta plus sin theta, for time being we can take it out. So we can combine a cos theta I plus a cos phi sin theta j. If I combine these two, then it becomes a cos phi alpha. Alpha is a direction where that is theta from x axis and along this direction. So if this is a circle, if this is a xy plane circle and this is a and this is phi, if it falls on xy plane at theta, then this vector is alpha. If this vector is alpha, then the gradient vector is a cos phi alpha, not I or j. A cos phi alpha minus a sin phi k, where the alpha has two components as alpha cos theta I and alpha sin theta j. This is what we were seeing. So alpha, so a, so the if I break the alpha now, then it will become a cos phi cos theta I plus a cos phi sin theta j. Okay, same thing what we were getting when we were doing the gradient vector. So a cos phi cos theta I plus a cos phi sin theta pi. If I add these two, then it becomes a cos theta in braces cos a cos phi and in braces cos theta I plus sin theta j. So cos theta I plus sin theta j I can combine together as alpha vector. So a cos alpha minus a cos phi alpha minus a sin phi k is the gradient vector that we are seeing, that is in alpha z plane. If that is true, then this gradient vector and the vector what we had a sin a cos a sin phi alpha, a cos phi k. Now if I do the dot product of these two vectors, so displacement vector what we are seeing is a sin phi alpha a plus a cos phi k, and now it is a cos phi alpha minus a sin phi k. If I do dot product, then they become 0. So now if I see the kind of a sphere, then if I have a radius center and at any point if I draw the displacement vector, then it becomes radial. This is what we are seeing. It is radial. If I find the center of this sphere, from center any point, the any point in a spherical coordinate it is r, phi and theta, whereas in Cartesian coordinate it is r sine phi cos theta I plus r sine phi or a sine phi sine theta I and a cos phi j, a cos phi k. So that is the coordinate of the any point. So it is radial. Any coordinate I take from the center, it is radial. If it is radial, then the gradient vector at any point is tangential, because from radial, if I take 90 degree, then it is tangential. Tangential in what direction? If I have a radial and if I take the perpendicular to it, then it comes like this. So if this is radial, then if I take perpendicular to it, then it is like this. That is tangential. But tangential can be any direction. So I believe this is better sphere. This is North Pole and this is South Pole. So in that case, if this is the radial, then this is tangential. But tangential to dash radius all are in 90 degree. Which one tangent we are interested in? So if I am taking alpha z plane. So if it is phi, then phi sine theta is alpha z plane, then it is from theta, it is x-axis. If that I am taking, then I am taking, okay, if theta is 90 degree, then it is yz plane. Theta is 0 degree, then it is xz plane. This is alpha z plane. If it is alpha z plane, then the tangent we are talking is not everything. It is in alpha z plane. So if it is like, if I have phi as 0, then gradient vector is a cos phi alpha minus a sin phi k. If phi is 0, then only the alpha component remains. That is a cos phi. So phi is 0 means a. It has magnitude of a, and then it is in direction of alpha. Alpha is bound with the theta. So if theta is 0, then it is along x-axis. So if it is xz plane, then tangent is like this, that is moving along the x-axis. If phi is 90 degree, means if phi is 90 degree, then it is in xy plane. If that is the case, then alpha component is 0, only k component remains, that is 1. So that the gradient vector moves like this in xz plane. In any alpha z plane, then gradient vector would move like this, where phi is 90, then it will be completely along the z-axis. So it would move from the flat, means parallel to xyz plane, and it will move slowly like this. This is the gradient vector that is tangential to the surface. And in the alpha z plane, it is not available in any of the book. Whatever we are talking, absolutely it is not available. From the root only it is not available. Calculation of the gradient vector from the spherical coordinate system and Cartesian coordinate system through the parametric vector is not available at all. This topic is not there. Anyway, you can search. So we are talking now. So whatever we are getting the gradient vector, that is in alpha z plane, and that is tangential to the surface. Whereas the displacement vector is a radial vector, that is 90 degree to the alpha, 90 degree to the gradient vector. So that is the concept that we are seeing. Little bit I'll continue, then it will be a kind of next session. So now can we see that what we try to find out? The gradient vector where the variation is phi, then we try to take out the gradient vector along alpha and alpha component and z component. Now if gradient vector alpha is a cos phi, then I component of the gradient vector will be a cos phi cos theta, a cos phi sin theta. Those are the x and y component of the gradient vector, whereas the gradient vector's k component is minus a sin phi. So that is the gradient vector. What about variation? Variation with uh, variation with phi that we saw, and what about now variation with theta? Variation with a, that is radius, variation with r, and variation with theta. If these two variations are concerned, then what would be the result? What all together? Gradient vector with variation in phi, variation in theta, and variation in r all together. Let's see what is the concept of variation with theta only, not phi and r. So if I have I component as a cos phi cos theta, a I'm sorry, a, okay, so I am talking about displacement vector, not the gradient vector. A sine phi cos theta I, a sine phi sine theta j, a cos phi I direction, j direction, and k direction. This is the displacement vector, keeping only theta as variable. So if that is the case, then if my function is f r phi theta, then dif r phi theta by d theta, then it will come as a sine phi sine theta I plus a sine phi minus, I'm sorry, a sine minus, sorry, a sine phi minus sine theta I plus a sine phi cos theta j plus 0, because a cos phi is the sine, is the k component, there is no theta, so no differentiation. So what we are trying to calculate is if there is any point that is a kind of where independent variable is r, phi and theta, so the kind of the parametric vector is fr phi theta, or r is the parametric vector, then r phi r r r phi theta. So r doesn't look good here because r we have taken as variation of the radius. So I would say any function called h. So h is a kind of a parametric vector, then h r phi theta, so dh by d theta, dh by d theta we are calculating. So h r phi theta equal to a sine phi cos theta I plus a sine phi sine theta j plus a cos phi k. If I am calculating dh by d theta, then it will come as a sine phi minus sine theta I plus a sine phi cos theta j plus 0, because a cos phi doesn't have any theta. If that is the case, then it is like we are trying to calculate velocity vector for a circle. If I have a circle and its equation is in a way that radius is a sine phi, if radius is a sine phi, then a sine phi cos theta I plus a sine phi sine theta j, then the velocity vector will be a sine phi minus sine theta I plus a sine phi cos theta j. So now if it is, don't you see this? If it is vertical, it is phi. If phi is constant and a is constant and theta is variable, there only it make 360 degree. If phi is 90 degree, then along xy plane it is making 360 degree. In xy plane it is making 360 degree. In xy plane it is making 3, it is fixed. So in xy plane it is making 360 degree when phi is 90 degree. If phi is 0, there only it is rotating like this. If phi is some angle, then there it is making like this. If I turn it like this, then it will make something like this. If it is 90 degree, then come, okay, if it is 90 degree, then complete it will make like this, but it is theta, then it will make like this. I mean, understandable. If I take the actual, this is vertical and this is theta, then it will be like this. If theta is 90 degree, then it will be like this. If that is the situation, then we are talking about a circle which has a radius xy plane. Everywhere cross section is xy plane. If I have a phi, so if this is vertical and this is phi, then we are talking about this xy plane where the radius is a sine phi. So if that is a circle, then we have a circle. If that is a circle, then we have a circle. This is a circle. Now, when phi is 0, then circle is point or nothing. But when phi is 90 degree, when phi is completely 90 degree, circle is very big. But if phi is something, then we have a small circle somewhere. So, if I have a sphere, you can consider this that we are chopping along the z-axis as per the phi. So this can be said as contour, cross section along the z-axis. So if cross section is less, if cross section is less, then the circle means if height is less, in a sense, if there is some phi angle, the circle is small. What about the radius of the circle? That is a sine phi. Then x component is a sine phi cos theta, a sine phi sine theta is the y component. Now if I calculate the velocity vector, then it will come as a sine phi minus cos theta minus sine theta I plus a sine phi cos theta j. So if this is a circle, and this is radial vector from center, radial vector is kind of going out of the center, 90 degree from the surface. Then if that is true, then if this is the circle, then these are the radial vector. If this is the circle, then this is radial vector. From the center it is going along. If that is true, then gradient vector is tangential because it is 90 degree. Obviously, right? If I have a cos theta I plus sine theta j, and then I have minus sine theta I plus cos theta j, if I do the dot, it becomes 0. So if it is 2D plane, then it cannot go anywhere else. If this is the radial, then perpendicular is the tangent. So if I have a 3D where I am at phi degree, then we land up in a cross section circle. Then if I am varying only theta, not phi and r, then tangent would move, then gradient would be tangent to the circle and it would move like this. So if I see the 3D, earlier when theta was constant, r was constant, radius was constant, then only phi was moving. Then if this is the radial of the displacement vector, then gradient vector was tangent and it was moving like this. If I keep r constant and phi constant and theta only moving, then wherever the phi is, then it will move like this. If I take this cross section as a circle, then along the circle it would move, the gradient vector would move like this. So gradient vector, if it is, I chop it, then gradient along this gradient vector would move like this. Okay, this is theta variation. If phi variation, then gradient in that alpha z plane, gradient would move like this. If there is r variation, then we will see. Altogether, we will see. Then in 3D with other example, we will see. 2D other example, we will see. Then we will see the algebraic form, Cartesian form only, then gradient vector, and then what are the anomaly we are seeing from the spherical coordinate and parameterized vector and Cartesian coordinate, and then algebraic equation calculus, those anomaly also we will see. So that we will see.